So now that we've learned a little bit about how to evaluate limits algebraically and analytically, I want to look at some more advanced techniques for doing that. And the first idea I want to talk about is equivalent limits. Now the two limits I have here are equivalent. They both equal e. We experienced these limits when we were working and evaluating limits numerically, and we found that both of these approach the value of 2.71, which is e. And these limits are the definition of e. E by definition is this particular limit. So what I want to do here is I want to show you that if I take one limit, so let's assume for a moment that I know the value of this limit, and let's suppose I'd never heard of this one. What I'm going to do is show you that through some substitution techniques, we can in fact show that this limit is equivalent to this one. Alright, so I'm going to begin, as I indicated, with a substitution, and I'm going to use a reciprocal substitution. I'm going to let 1 over x equal a variable a, 1 over x. And my strategy here is to rewrite this entire limit in terms of a. So that will include needing to change this. And I know that as x goes to infinity, if I look at how a and x are related, as x goes to infinity, 1 over infinity is going to make a approach 0 from the positive side. So I'm now going to rewrite my limit in terms of a. So my limit, this gets replaced by the equivalent expression here. 1 plus 1 over x is a. And the exponent x, if I solve for x here, that would mean 1 over a. And so this new limit I have is equivalent to this original limit because I've just made equivalent substitutions. And so this limit here would have to equal the value of e. And so I've shown that this value is indeed equal to e as well. Alright, here's another limit that I want to evaluate, and I'm going to do so using a substitution involving a reciprocal. Now just before I begin, I actually do know how to evaluate this limit from strategies we've talked about, and we can do that by remembering that if x is going to infinity, these are of lesser significance in the numerator and denominator. That leaves us with 2x over x, in which x cancels, and therefore the limit of the 2 would equal 2. And so we know the value of this turns out to 2. When you might want to do an equivalent limit is when perhaps you don't know how to or don't remember how to evaluate a limit the way it's given. So you can change the look of the limit into an equivalent limit, and if you can then get the answer to that limit, you will then have the answer to your original limit. Alright, so when we're doing a substitution, we always begin by creating a variable. So we're going to let x equal 1 over a in this case. And we are going to need to replace the x going to infinity. As x goes to infinity, if this was infinity, a would be close to 0 from the positive side. Okay, this is looking good because we're getting similar to what we were hoping for, a variable going towards 0 from the positive or negative side. I'm then going to do my substitution. So my limit as a goes to 0 from the positive side of, okay, so x is 1 over a, so that's going to be 2 over a plus 1 over a minus 2. Alright, let's simplify this expression. I can do so by multiplying numerator and denominator by a. And so that would equal distributing 2 plus a over 1 minus 2a. And so this limit is equivalent to this limit. They both have the same value. They both have the same answer. So if I then evaluated this limit, let's make a approach 0. That would be 2 over 1, which is 2. And since this limit has a value of 2, we would know that the original limit had a value of 2. Just a couple more examples related to the limits and strategies we were talking about in this video. you'll notice that this limit is very similar to this limit for e. The only difference obviously being that we have a 2x here. So the question is, how does that affect the answer to this limit? So a common strategy when you have something that's very close to something you already know, which is this, is to rewrite the question in terms of the other limit and make an adjustment. So what I'm going to do here is I'm going to rewrite all this part's fine. Now I wish this was just an x, so I'm going to leave it as an x, and then I'm going to take advantage of the fact that I know by power rules or by exponent rules I could write that expression like so. You might also remember that we also know that the limit of a root of something is equivalent to the nth root of the limit of that function. And since roots are really exponents, we know therefore that this is equivalent to that entire power of 2 can be applied to the entire limit. And therefore we know that all of this is e, and so the value of the limit is e squared. Alright, here we have another limit that looks very much like the same limit above. We know, once again, the limit as x goes to infinity. We know this. This limit looks similar. Alright, now the concept here is that these two sections right here are reciprocals of one another in the limit for e. So what I'm going to do is I'm going to rewrite this limit to look similar to the concept of this limit. So I'm going to write limit as x goes to infinity of 1 plus 5 over x. Now I would want my exponent to be the reciprocal, so let's just put x over 5. But now we got to be mindful of the fact that the exponent is really 10x. So on the outside here, I know that if I put something on the outside here, these two things have to produce 10x when I'm all done. And I can get that by putting 50 here. Alright. Now the other question you might ask is the fact that this is 5 over x and this is x going to infinity, does that in any way affect this from being e? And the answer to that is no, it doesn't, because as x goes to infinity here, x over 5 is still going to go to infinity, not just as fast, but we're going to infinity. We're going to a never-ending amount. So yeah, this is still e, and then to the power 50.